Hey, welcome to 49cc Scoot. My name's Brent. I've been looking for a Torsen arm to add to my RC1, but the options that I've found were all around $200 or more with shipping, so I'm gonna make one. If you're not familiar with them, a Torsen arm attaches to the engine case at the exhaust mounts, and a special sort of nut-shaft combo is attached to the rear axle and rides in a bearing in the arm. The intention is to add support for the transmission and the engine cases that act as a swing arm, which is said to improve handling, decrease asymmetrical tire wear, reduce the risk of crankcase failure, and may even make performance more consistent and improve the operation or longevity of transmission components. My original plan was to make something pretty close to everything I've seen for sale, using a sheet of 3/8 of an inch thick aluminum for most of the part, and then an additional bolt-on piece to hold a bearing. I priced out the main supplies at about $120, and I thought it was more trouble than it's worth that way, because precision placement and fit of the bearing in a large chunk of aluminum would be pretty difficult for me. 190mech from the 49ccscoot.com forum suggested using steel tubing for most of the arm instead, to potentially cut down on cost and have something that I could weld together, while hopefully making the fabrication process a little bit easier. I'll be using a 6204 2RS bearing for the axle shaft to ride in, because it's a common bearing with a 20mm inside diameter. This 2.5 by 1 inch steel disc will be turned into a holder for the bearing. I would have preferred to use a piece of pipe or tubing instead of a solid disc, because that would save a lot of time, but I didn't see anything that worked with the dimensions that I was looking for. 6 inches of hardened 4140 hex bar should be plenty to make a custom axle nut shaft, even if I mess up once. I bought 3 feet of 1/2 inch tubing with 83 thousandths wall thickness, and 3 feet of 1/2 inch with 65 thousandths wall thickness. It would be cheaper to buy a 6-foot length of one or the other, but shipping 2 3-foot lengths of tubing cut the cost of shipping significantly. I was planning to use the thicker tubing for most of the arm, and I thought that if I needed to add additional cross bracing, maybe I could save a little weight and still have something sturdy enough with the thinner tubing. I got these retaining rings in case I needed them for the bearing housing, basically because I've seen them used on Torsens for sale. And these M8 by 1.25 by 80mm bolts will hopefully be long enough for however the Torsen arm and exhaust end up being mounted. To spend $150 or so to build a Torsen arm versus roughly $200 to buy one, you have to want to do it for the experience or to have something custom, because otherwise it will be well worth a $50 difference to save yourself a whole lot of time in the shop. I started off with probably the easiest job in the whole project, turning a couple of pieces of 1-inch steel rod into mount adapters. I cut a small indentation into the back of each one to help them sit on the engine mounts, with 40 to 50 thousandths of an inch of wiggle room. I thought that way, if spacing becomes an issue, I'd be able to cut them deeper as needed to move the arm in, or I could make spacers to fit in the indentations. Next, I took on what I assumed to be one of the toughest parts of the job, making the bearing holder. I began by facing the disc down to a 23mm thickness, so I'd have room for the bearing, a back wall to act as a stop, and a retaining ring groove above the bearing. I cut the outside diameter down to 55mm, leaving room for thick walls around the bearing. I drilled and bored a 30mm through hole so there would be an opening in the back to help remove the bearing and so that the shaft could come through the bearing without running into the wall. Then I started working on the bearing bore, taking off just 10 thousandths of an inch most of the time to reduce stress and hopefully create less flex. This is the part that makes the bearing holder tough, because bearing fit has pretty specific needs, so you can't miss the mark on the bore by very much at all. In this case, I was aiming for somewhere between 7/10 thousandths to 1/1000th of an inch of interference fit, so the bore needed to be that much smaller than the bearing's outer diameter in order to create a press fit that holds it in place. I don't know what that's like on a big high-quality lathe, but on a Chinese mini-lathe with plenty of flex, it's a bit stressful as the finishing cuts approach. I wound up with a 1.8495 inch inside diameter as near as I could measure to the back wall of the bore, which would give me a .00089 inch interference fit. I did have taper in the bore though, with the outermost section about 1.5 thousandths of an inch larger. I spent the time before boring to use an indicator and get it to read 0 as I moved the compound slide across a greater distance than I'd be boring, and the carriage was locked down with as much play as I could take out of the cross and compound slides. So it was set up as well as I know how to get a straight bore, but this has always been my experience with the mini-lathe. The carriage should run true, but the carriage on this thing flexes as it's moved, so it wasn't a good option when needing a very precise bore diameter. Since the bearing fit seemed okay, I decided that I shouldn't need a retaining ring, and I cut the holder down to leave more room for clearance if needed. I pressed the bearing in and the fit felt good to me. That's not exactly scientific, but it took enough force that I think it will be secure, and not so much that it seemed excessive or affected how the inside of the bearing rotates. If you need parts for your scooter, check out ScooterTuning.ca. They've got performance parts, replacement parts, pretty much anything you would need or want to maintain or modify your scooter. They don't just have fast shipping and competitive prices, they also support this channel. They give me a bit of a discount on parts, and that is very helpful because it allows me to test more things and keep my projects going. So if you enjoy the kind of content that I make, then please check out ScooterTuning.ca. Next up is the other tough job of the project, making the adapter to replace the axle nut. I've made custom nuts before and found that it can be pretty difficult to get them to be true when threaded onto a shaft. I think it would be less of an issue if I were cutting threads with the lathe rather than using a tap, but I have figured out a process that tends to work for me, so we'll see how it goes. I started by taking measurements of the hub and wheel to figure out roughly how long the adapter would need to be. I cut a piece at 2.8 inches to leave more than I really thought I'd need even after facing, and then began trying to get the bar as true as I could in the chuck. Then I faced off one end and center drilled before switching to a 1/2 inch bit appropriate for an M14 by 1.5 tap. The drilling process started about as expected, but quickly got very difficult and time consuming. I quit filming very quickly, but it took me hours to go 1.25 inches in because the lathe kept popping the circuit breaker and jamming up. The lathe was struggling before even making contact with the cutting tip, with just the friction of the sides of the bit against the walls of the bore, so I switched to a bit one size smaller to finish. I tried going back to the 1/2 inch bit, but it was still seizing up before reaching the cutting point, and I figured it should be fine for tapping, so I put the tap in the tailstock and started it. Then I switched over to a T-handle briefly before using a ratchet adapter to finish. I threaded a bolt in and it was really wonky. I think the ratchet adapter was a big mistake because it's easy to apply force to one side and drive the tap off center. I also wondered if I was boring in straight because the drill bit kept seizing up in the already bored section. I talked to 190 Mech on the forum later, and he told me that 4140 will work harden at the cutting edge and dull bits, with only carbide being able to cut through effectively at that point, so I'd be better off to go up in steps with drill size instead of going straight to a 1/2 inch. I flipped the hex bar around for a practice run on the opposite side instead of risking ruining the leftover material that I'd need to make an adapter, and went through the same truing and facing process. I used a number 4 center drill and then started with a 5/16 of an inch bit from a set of stubby drill bits that I bought to try to decrease flex. I moved up to 3/8, then 7/16, which started to get more difficult. I took a smaller step up to 15/32, which was back to being easy, and then finished with a 1/2 inch. Drilling in steps was incredibly simple and uneventful compared to going straight to 1/2 inch. I started the tap in the tailstock till the lathe couldn't handle the load. Then I turned the hex with a wrench till the chuck could no longer keep the tap from rotating since it was chucked on the round section. The tap had an indentation in the center, so I swapped the chuck out for a dead center and used the T-handle to hold the tap while the center was pressed against it to keep it straight and finished tapping. I threaded in a bolt and found that it had 4.5 thousandths of an inch of run out when I measured it about 3 inches out. Not perfect, but I can deal with that much run out. For comparison, the first try had 199 thousandths of runout measured the same way. Now all I had to do was repeat the process on the remaining chunk of hex bar. I got through tapping and the runout was good enough, so then I cut the head off of an M14 by 1.5 bolt and screwed the part onto that. The idea is to have a true shaft with threads on the end, just like what the nut will be installed on, so the remaining cuts will be straight relative to the threads when used. Now if you can cut the threads true in the first place, then this wouldn't be necessary. But I've made multiple attempts this way and I've never had one come out right on, so finding a way to get the nut true is important since it will be rotating at high speed and needs to stay aligned with the bearing bore. The initial facing attempts didn't go well, breaking the tips off of a couple of carbide inserts. I switched over to a ground high-speed steel bit because I think the edges of the hex stock colliding with the thin carbide inserts was just too much. I made an indentation and then used a live center in the tailstock because I was seeing the piece deflect as I tried to cut it. Once the hex was rounded off, I switched back to carbide. Many of the adapters that I've seen sold have the hex area somewhere near the center, but it seemed easier to me to keep it near the hub and leave a solid base. The only disadvantage of doing it this way to my knowledge is that it would be easier to install the wheel and hub as an assembly if the hex section was past the wheel, but I usually take the wheel off first anyway. I had a 0.5 of an inch of runout when finished, so I was happy about that, but I missed the mark a bit on diameter. I was aiming for a 2000 slip fit, so the shaft would be just a little smaller than the bearing's ID. I wound up with 2.5 to 3.5 thousandths on most of the shaft, again because I can never get a totally straight cut on this lathe. The very end of the shaft was larger than I wanted and I had to force the bearing to start. But the shaft was too long anyway, so I cut a bit off and faced it. Next, I wanted to get the Torsen arm framed up. I started by using a piece of tubing to check the alignment of the bearing holder and mounts, and found that the mounts needed to come out a bit, so I made up a couple of 0.4 inch thick spacers. Then I notched one end of the thicker walled tubing to match the bolt-on mounts. Since I don't have a tubing notcher, I used a 1-inch hole saw in my drill press. It seemed easier to me to match the angle at the bearing holder by hand, especially after seeing how much my 2 1/8 inch hole saw wobbled. I taped one end in place and used the clamp to keep the other end where I wanted it and tacked the top tube in place. Then it was the same process for the lower tube. I made up one crossbar for the front to box it in, and then put ugly welds on everything that I had done so far. I'm not sure if I warped something while welding, or maybe removing the bearing before everything was welded, but it wanted to sit a little further in on the bearing. It still aligned okay, but that made clearance very tight with the wheel. I made up a couple of 550 thousandths thick spacers to replace the 400 thou spacers, and that gave me plenty of room. The next task was figuring out how to get an exhaust to mount while using the Torsen arm. My engine was apart for months waiting for a piston, but that piston just happened to arrive right as I needed to put the top end on to see exhaust placement, so I hoped that that was a sign from the two-stroke gods that everything was going to go well from here. But as soon as I put the pipe on, I knew I had messed up. The pipe would hit the bracket and its lower mount if I tried to swing it in. I looked at other Torsens and realized that they have an upward shift right after the lower mount to create more clearance for the exhaust. There's now a long axle nut with a bearing sticking out of the wheel, so I won't be able to tuck it in like before, but it shouldn't have to stick out this far. I really should have mocked the cylinder and the pipe up before I started and paid attention to how everything fit together, but at this point I was left with two options. I could leave it as is and call it close enough, or I could spend a bunch more time chopping it up and reworking it to make it fit at least a little bit better with the pipe. Well, three options. I could give up and buy a Torsen. But as tempting as that was, I wanted to see this through and wind up with a part that I'd like, so the only option for me was to start cutting up the bracket. The front cross brace would need to be moved as far forward as I could get it, and the front of the lower leg would have to be cut out so I could make it angle upward. This is when I realized that it would have made a lot more sense to test fit while everything was still just tack welded, so it could have come apart more easily. But at the time, I wanted the frame welded so it wouldn't get shifted while I tried to figure out any cross bracing and exhaust mounting add-ons. I also needed to grind away part of the lower mount for clearance. I checked fit when the lower section of the Torsen was removed, and the pipe could go in quite a bit more, but the entire Torsen would have to be redone to keep it that way when framed in. Some of the aftermarket models swoop up and then back down to allow clearance for the exhaust, and I think that's what would need to happen to really tuck it in tight, but I continued modifying this one. The front brace attached directly to the mounts for maximum clearance, making sure not to place it so far forward that it would hit the ignition cover. Then I added the lower section with an upward angle, trying to compromise between clearance and what I perceived to be stronger. I was afraid that if I made the lower frame come all the way up to meet the upper mount, that it wouldn't be as rigid as having it boxed in, but I'm not sure how much it would really matter, and exhaust clearance wouldn't change a lot either way. I checked fit, which was a little better, but not a lot different, and then moved on to adding a cross brace to connect the joint in the lower section to the top. I thought I was finished at that point, but then decided to add another piece to try to spread the load across the front bar a little better, since I had room above the pipe in that area. Okay, I think that's finally it for the Torsen arm, and even with a bit of a redo, I only used one 3-foot length of tubing, but it still needs a mounting point for the exhaust. I definitely wanted to isolate the pipe from some of the vibration that comes through the mount and allow it to flex a little bit. Most exhaust manufacturers do this, and I was sort of a stress tester when John, 190 Mech from the forums, was building some scoop pipes long ago. I saw then that solid mounted pipes were way more likely to have stress cracking and failures, and just adding bushings pretty much eliminated those problems, so it's not something that you want to skip. My first thought was to use an available bushing, and I had a bushing from a GY6 on hand that had an 8mm inside diameter to match the 8mm mounting hardware for the pipe, but it was very rigid. I looked online briefly, but didn't see many options that I liked or would be cost effective, so I wound up using homemade bushings just like John did for his pipes. I needed a centerpiece for the bolt to go through first, and by pure luck, the 83 thousandths wall thickness half-inch tubing that I used for the Torsen was a good fit. I cut off a chunk and machined the end straight so it came out 1 inch long. It could be shorter, but I knew the pipe would need some spacing anyway unless I made a mounting tab stick out a lot, so I might as well take up some of that room with the bushing. Then I had to find a piece of rubber hose that would fit somewhat snug over the tube, so I got out my bin of hoses and found half-inch heater hose that worked well. I also needed hose large enough to fit over the heater hose, and I had what I think is 11/16 hose that I could make work. 3/4 inch would fit a bit easier, but I didn't have any on hand. I cut the half-inch hose just barely longer than the center section. You could match it up exactly, but a little compression when tightened seems good in my mind. I needed to cut off 2 pieces of the 11/16 hose, but my hose cutter isn't big enough, so I stuck a piece of steel rod in the hose and marked the length. Then I wrapped masking tape around the mark to give me a guide for a straight cut. I used a sharp razor knife and sprayed a soap and water mix on the hose and blade to act as a lubricant. Plain water should work fine, but I had this spray bottle right beside me. Then I just followed the tape around with the razor. This is a simple way to get a clean cut on hoses without special tools. A piece of the large hose then needed to be installed over the smaller hose, and the 11/16 was a tight fit, So I backed the steel tube out a bit so the 1/2-inch hose could flex, and heated the large hose a little bit with a heat gun briefly before pushing it on. It shouldn't be installed right now, but I pushed the other end on as well so you could see the idea of this bushing if you hadn't figured it out already. The hose going through the mounting hole will isolate the bolt there, and the larger hose pieces will prevent direct metal-to-metal contact between the bracket on the Torsen and the exhaust or its fastener. Once that was done, I put a long bolt through the pipe's mount and put the bushing along with some washers I was going to use on each end on, and tightened it, keeping it roughly centered in the elongated hole in the pipe's mount. I only used 1/2 of the outer hose, so I could see where a tab would need to be to work with the bushing. I made a template out of a cereal box. Then that was transferred to 1.5 wide, 11 gauge steel flat bar. I drilled a 3/4 inch hole and took some time to smooth all of the edges so it wouldn't cut the rubber hose. I tacked the bracket on with the mock-up bits in place and then finished welding in a vise. You can see here that I have good alignment of the exhaust mount and the tab on the Torsen. This is important because if you have to force an exhaust into place, you are introducing stress that can cause problems with cracking, welds breaking, and things like that. I noticed that some aftermarket Torsens use a special ring on the axle shaft that is similar to what some Piaggio 2-strokes and the RC1 use on their primary drive shafts to interact with the CVT cover bearing. I only knew to call these compensator or compensating rings because that's what Piaggio calls them, and I hadn't seen them anywhere else. The many Moreira clones that I've had have all used a standard drive shaft support with a shaft directly in the bearing, and all of those have eventually worn enough to cause rattles and poor contact. On the flip side, the RC1 with the compensator ring has had no trouble so far and still fits well after a couple of years of use, so it seems like it would be a pretty good feature for the Torsen as well. The only problem is, I couldn't find them at any hardware suppliers that I checked in any size, and the Piaggio part is way too small. I spent some time searching and found 20 by 20 millimeter rings sold for a Cosmos 300, which is a 2-stroke paramotor engine. I'm using a 20 millimeter ID bearing that's 14 millimeters thick, so the ring is wider than the bearing is, but I don't see why it should matter much if the ring isn't all covered by the bearing. I would need a groove in the shaft to accept the ring, but I don't know of any source for specs on fit, so I had to figure it out on my own. Rather than experiment on a part that took me a long time to make, I cut a piece of aluminum to the same diameter as the axle shaft that I made. Then I started cutting a groove and doing a test fit, and cutting more and checking again. The ring's ends would butt together or have to overlap, which didn't seem correct. I looked at the RC1's drive shaft to be sure, and there was a gap between the ends, so I cut the ring with tin snips as needed to maintain a small gap while I continued testing. Eventually, I wound up with a snug to tight fit. I took measurements and the groove was 800 thousandths of an inch long with a diameter of 706 thousandths. So all I had to do was replicate that on the real part. Installation was more difficult because I couldn't easily compress the ring with my hand due to clearance, so I used a zip tie to hold the ring while I tried to start it. I actually cut it about a 1/2 thousandth larger diameter than the test piece, and it was a little tight and I had to tap it on. But maybe it was just a little harder because both ends of the arm need to remain aligned during the actual install to make it go on straight. Everything still moved freely, so I decided to call the fabrication done and move on to giving the part some rust protection. I sprayed the arm with a few coats of clear so I could keep the natural, sort of ugly but interesting look. I didn't want layers of paint on the axle nut, and I wouldn't expect it to hold up well anyway, so I heated the nut and dipped it in motor oil instead. I've done this a couple of times before, and it gives some rust protection and I can get interesting coloring. I rode about 6 miles and discovered powder coating taken off of the wheel from contact with the Torsen. I was surprised to see that the arm was sitting outward as it was before the ride, with plenty of clearance. So I guess the arm must walk in and out to some degree from vibration and probably other forces. After a small amount of research, I realized that there's a reason for aftermarket axle adapters having the hex section out away from the hub. Initially, I thought it was just for convenience of removal and installation, but while it may serve that purpose, it also works as a stop, often in conjunction with spacer washers, to prevent contact with the wheel. I made up a couple of aluminum spacers in hopes of fixing the problem. I used aluminum because it's easier and quicker to work with, but also because I hoped that if anything wore, it would be the spacers instead of the axle or the bearing. I had to use a two-piece design because the compensator ring couldn't be installed with a single spacer. The first part fits over the axle adapter somewhat snug, and then the ring can go on, and then the second piece goes on over that. I took a couple of test rides and no longer had trouble with contact. It's just a shame that I didn't learn about the necessity for a stop before chewing up the wheel. In the end, I can't say that it was worth all of the effort to make my own Torsen arm, considering the expense for supplies wasn't all that far off of the cost of a bolt-on Torsen. Then the damage to my powder coating made it much more expensive if I get that repaired. But I hope that I learned a lesson for all of us so no one else has to have the same issue if you try this. Time will tell if there's any discernible difference in tire wear or performance, but I think it is a good idea to support the engine case and axle more in general, so as long as there's no catastrophic failure, it's a good addition in my opinion. If you've enjoyed watching this project or found the information useful, please give the video a like and subscribe for more content like it. Thank you for watching.